Okay, in this video we're going to continue building up the periodic table one electron at a time. Well, let's skip a few. Anyway, we ended the last video by building up period 1, which is hydrogen and helium, and most of period 2, and we left off at oxygen, and now we're going to do the end of period 2. We're not going to do every single element. We're going to do neon, which has 10 electrons because it has 10 protons. And using the Aufbau principle, we start at the bottom. 1, 2, 3, 4. Because of Hund's rule, the p orbitals are filled one at a time before they are doubled up. And when we have 10 electrons, we find that we have completely filled that 2p orbital. And so the noble gases in general will fill an orbital. For helium, it's the 2s orbital, but for all the rest of the noble gases, they'll be filling a p orbital completely when they end the row. So they are filled p orbitals. Okay, now let's continue on with the next row, which is period 3. And with period 3 now, we have added the 3s and 3p to our diagram here because we will start putting some electrons in those. The first element we're going to do is sodium with 11 electrons, 11 protons, 11 electrons. And so we follow the same rules. Hund's rule applies here. I can't see that one. And then we have one more beyond neon. So there's one electron in the 3s orbital. So we can write our configuration for sodium as 1s2, 2s2, 2p6, and 3s1. One electron in the 3s. And let's jump a couple over to aluminum. It has 13, so we'll fill exactly how we did before. And then we have to do 1, 2, 3 more electrons beyond the neon configuration. So that has 1s2, 2s2, 2p6, 3s2, 3p1. Alright, and you should be able to do all the others up to argon, and we'll find argon has 18. Again, we do start out as before, and when you count out 18, you will find that just like neon, you are going to have all the p orbitals filled. This time it's the 3p. Okay, for neon it was the 2p. And for the next row, which is argon, it's the 3p. Okay, and the full electron configuration here, 1s2, 2s2, 2p6, 3s2, 3p6. All right. Now, try one yourself. Draw the energy levels, just like I did, and the electron configuration for chlorine. So go ahead and stop the video and do that. And now I'm not going to do the energy levels. I think that's it's one less than argon, but the configuration 1s2, 2s2, 2p6, 3s2, and 3p5. So it's one less than argon. Okay, now as you'll notice, these electron configurations are getting longer and longer as we go down the periodic table, and they get quite long at some point. So we have a way of condensing the configuration. So we have a full electron configuration, which is the ones we've been writing, and here it is for chlorine again. And then we have a way of writing it more condensed. Okay, and the way we write it more condensed is we write down, we notice that all the way up through here, we have the configuration for neon. Okay, we have completely filled the noble gas configuration for neon, so we basically go back to the last filled noble gas configuration, and instead of writing it all out, so I'm writing this all out, we simply put neon in brackets, and that means the electron configuration of neon. And then we write the additional electrons after that. Okay, and the The condensed configuration for fluorine, the nearest noble gas configuration is filling the 2s, and that is helium. So the condensed configuration is helium, and then what's left over I just made a mistake. I'm sorry. I made a mistake there. Hope you all noticed that. Helium is only the 1s. That is a mistake. The 1s is helium. And so the 2s and the 2p need to be written here. So I will fix that. What's beyond the helium is 2s2, 2p5. Okay, so let's have you try one. Write the full and condensed configurations for magnesium, so be sure to stop it and work on that. All right, the full configuration. Magnesium would be 1s2, 2s2, 2p6, 3s2. How do we write that condensed? We notice that up through the filled p orbital is the configuration for neon. So we write neon in brackets, and we write 3s2 after that. All right, and now I want to bring up the concept of a valence electron. Or valence electrons. And this again is neon. So valence electrons are some of the electrons in your configuration, and what they are is for the main group elements. We're going to only talk about those. For the main group elements, the valence electrons are all those after the noble gas configuration. Okay, so these are the ones of the highest n value. In other words, here we have n equals 1, we have n equals 2, and the ones of the highest n value are the valence electrons. Okay, so these are valence electrons, and that's going to be an important term. We'll go back up and look at some of these others. So for fluorine, the n equals 2 levels are the electrons, are the valence electrons. So everything after the noble gas, and again, that's only for main group elements, not for transition metals necessarily. All right, after we get past the third row, we just finished the third row, it turns out things get complicated because this is the order of levels in energy. We go up with energy. We find that it's just what we did. We did 1s, then 2s, and 2p, then 3s, 3p, but now the next level is actually a 4s, because the 4 levels, the n equals 4 splits into s, p, d, and f, but they start overlapping with n equals 3. Okay, so the 4s is actually lower in energy than the 3d. And then you continue on with the 4p. Okay, so the energy levels start to overlap. And actually, the higher you get in n, the more overlap there is, and there's quite a lot of overlap. So we use one trick helps you know the order of the energy levels going up, and that trick is that you write the energy levels like this, so that all the s's are in one row, then all the p's, and then all the d's, and all the f's, and then you start drawing diagonal lines. Okay, so first you have a 1s, then you have a 2s. The next level after 2s is 2p, and then it's 3s. After 3s is 3p, but then after 3p we go to 4s, not the 3d. So 4s first, then 3d. After that, 4p and 5s, then 4d, 5p and 6s, etc., etc. So you can draw these diagonal lines, and these will tell you the order of filling of the energy levels going up. Alright, so another, instead of memorizing that though, there's actually, in my view, a better way to learn the order of the energy levels, and that's by looking at the periodic table and remembering that we have an S block and we have a P block, with the exception of hydrogen and helium, which are, helium is not in the P block, although hydrogen's in the S block. Alright, and then you have a D block, and of course down below you have an F block. Okay, so they're in these blocks, and then the rows, or the periods, are labeled going down, just like it shows in the S. And so the S levels and the P levels will be correctly labeled by numbering down the side. Okay, so the first one is 1, the first row is 1, second row is 2 for S and P. For the D levels, it's different. For the D levels, they are n-1 D levels. So if your n is 4, the D level is a 3, n-1. And then the F levels are actually n-2 levels, F levels. Okay, so this block, this line here, fits up into this line. So actually the whole periodic table should be separated, and the 4F and 5F should be inserted between the 6S, 7S, and 5D, 6D. Okay, so if n is 6, the S is 6, but the F is 4. It's 2 less than the 6. And then you jump back to 1 less than the 6 for the D. Okay, so you can actually just see the order by going across, counting up on the table. First 1, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d. So you just go across in the periods and you will get the right ordering of the energy levels. Alright, and finally I'm going to name some anomalies in filling, because things don't always get filled exactly in the order that you expect them to. And these anomalies, some of the anomalies occur in the d orbitals, some occur in the f orbitals, and so I'm going to show you a couple of important ones. The scandium, which has 21 electrons, I'm not going to draw all the energy levels. I'm going to start at the 4s level and show you 4s and 3d. Remember, 3d is higher than 4s. And so when we get to that point, we only have 3 electrons left for scandium. Okay, so there's a bunch of energy levels lower that I'm not showing. And scandium fills normally. It follows the Aufbau, first 2 and then 1. That's exactly what you'd expect. Okay, but vanadium also follows it. It has 5 electrons left at this point. And it fills, as you'd expect, following Hund's rule and Aufbau. Copper is the anomaly. Okay, copper makes an anomaly. And what it does is it actually fills 1 electron in the 4s, and then it has a total of 10 other electrons. And the reason it does this is because it gains some stability by completely filling this d orbital. So instead of putting 2 electrons down here and 9 up here, it puts 1 and 10. And that gives it a little bit of stability. So that's one of the anomalies, and there's others very similar to this.